Okay, so the block theorem indicates what is the general structure of the electronic wave function in case the Hamiltonian has this structure, so the kinetic term plus an additional potential term, and the potential term has the same symmetry of the Bravais lattice. So in this case, we have that the potential term in the Hamiltonian has the same periodicity of the Bravais lattice that is found in the system that we are going to study. In this case, the theorem tells us that a wave function can be actually found in this system, so the Schrödinger equation may be solved, and the general structure of the electronic wave function has phase times a sort of modulation of the phase. And the modulation, this U, has the same symmetry of the potential. So even if small u has the same symmetry of the potential, psi has not that symmetry due to the fact that psi is modulation times the phase, and the phase is not periodical in the direct space. So in this case, what we have is that just the modulus, the square modulus of the phase is periodical, not the actual phase. So the electronic wave function is not periodical in the direct space. In this situation, we have that the wave function depends on two indexes. One index is an integer n. The other index is, as you may see from the phase, a wave vector. And this wave vector is a sort of quantum number identifying the specific electronic level that corresponds to to a specific electronic wave function. So you may say that k, this wave vector, is let's say a constant of motion. So if the electron is described by these two quantum numbers n and k, those two quantum numbers in general may be considered to be a constants during the motion of the electron. And please consider just one thing. I make now this comment. The problem that was found in the Sommerfeld picture was a problem where the Hamiltonian was just the kinetic Hamiltonian. So that was invariant under translations. And that's why the momentum of the electron was a constant of the motion. In this new picture, so in the block theorem, the system, the Hamiltonian is not invariant under translations because we have a potential term, and that potential term depends on the position, and the dependence has a periodicity, that is this periodicity here, but that periodicity is not arbitrary. So that is fine just for translations that are equal to a vector belonging to the Bravais lattice. So that will have a consequence on the properties of the system, but due to that, the momentum is not a constant of motion. So if we obtain So if we apply the momentum operator to the electronic wave function, this is not that just a constant times the wave function. So this means that the momentum of the electron is not a constant of motion. Now, just a comment concerning momentum. Up to now, in the Sommerfeld picture, P was equal to h bar k. So in principle, k was not a momentum, was a wave vector. The momentum was h bar times k. But in the way of saying, in general, momentum and wave vector are synonyms in the Sommerfeld picture because there's just h bar between k and p. In this new configuration, so when we consider the wave function coming out from the Bloch theorem, the let's say, just to stress that the momentum p is not a constant of motion, but k, that is a wave vector, is an actual constant of motion because that is a variable that it identifies the wave function and then doesn't change during the motion. K is not labeled as, let's say, momentum, but is labeled as crystal momentum to distinguish that from the term momentum that I used in the Sommerfeld picture. So K is labeled as crystal momentum. And let's say, I know that sometimes I will miss the term crystal. So I know that in some situations I may forget to say crystal momentum and I will just say momentum. But please consider that from now on, K, to be consistent with the picture and with all the details, and then the meaning of K can be described and identified as crystal momentum to distinguish that again from P, momentum, that in the Sommerfeld picture was proportional to K. Now this condition fails, so we distinguish that by saying crystal momentum considering K. Now what can we say concerning K and N? Before discussing that and the value of K, just a comment concerning the boundary conditions of this calculation. The boundary conditions are the same that we used in the Sommerfeld picture. So again, we use the Born-von boundary conditions. In the Sommerfeld picture, the boundary conditions were applied on the two sides of the solid. So we just said psi of 0 should be equal to psi on the other side of the solid. And in this case, for instance, Lx, if we consider the x coordinate. In the case of the Bloch theorem, the idea is always the same. So psi of 0 is equal to psi of nk is equal to psi of nk on the other side of the solid. But due to the fact that now we know that the solid is not just a box, but is due to the presence of a lattice, the other side of the box is no more located at Lx, but is located at a distance from the origin that is the multiple of the lattice spacing. So if I call, for instance, N1 the number of ions that are found in the x direction, I multiply that by A1, that is the primitive vector along the x direction. In this way, I access, let's say, the other side of the solid. And the same condition is applied to 1 is the index for the x direction, and then 2 for the y, 3 for the z direction. So one tries to apply this condition that is again equal to the Sommerfeld one, but just rewritten to consider the presence of the lattice. And in this case, what happens if we consider the structure of the wave function due to the Bloch theorem? We have that psi nk of 0 is 1 times u nk of 0. That should be equal to e to the I k n1 a1 times u nk of 0 plus n1 a1. This, the modulation, let's say, is periodical. So this term and this term are equal with each other due to the periodicity. So we are just left with 1 equal to e to the I k n1 a1. Okay, now k at this step is again the wave vector describing the phase that is included in the Bloch wave function of the electron. K now, let's say, when I discussed with you about the meaning of K in the Sommerfeld picture, K was a wave vector belonging to the space of wave vectors. So we had the opportunity to define this wave vector space where we have the Fermi surface and so on. In this picture, we know that the Bravais lattice that is located in the real space has an equivalent in the wave vector space that is the reciprocal lattice. So the Bravais lattice and the reciprocal lattice in the wave vector space are related with each other. So we may think now that K, this parameter that we have in the phase, is located in the same space where we have the reciprocal lattice. Due to that, we may try to express K as a combination of B1, B2, B3 that are the primitive vectors of the reciprocal space. So as there is an equation that relates the primitive vectors in the direct space and the same vectors in the reciprocal space. It is that the scalar product is equal to 0 if the indexes are not the same, and if they are the same, we have 2 pi. Then using that, we have that I k n1 a1 is just equal to I. Then if k is this combination, the only term that survives is the term corresponding to index 1 in this case. So we have x1 n1 times 2 pi. This should be equal to have that the phase is equal to 1 to 2 pi times n1. I write that with a small n just to distinguish the large N, capital N, that is the number of ions in that direction, from small n, that is just an integer, an integer number. So what we have is that x1 is equal to, sorry, I forget the imaginary unit. X1, sorry, is equal to n1 divided by capital N1. So X is the ratio between an arbitrary index and the number of ions that we have in the X direction. Since you may apply the same calculation for Y and Z, what we have is that the arbitrary expression for K is N1 divided by capital N1 times B1. Then we have N2 divided by capital N2 by times B2 plus N3 divided by capital N3 times B3. So in this case, we have that the K wave vector is given by a linear combination of the primitive vectors in the reciprocal space. In general, it may happen that K is equal to a primitive vector, because if you set N2 equal to 0, N3 equal to 0, N1 equal to capital N1, then we have that K is equal to B1. So it may happen that the value of K is equal to a value of one of the reciprocal vectors of the reciprocal lattice, but the opposite is not the same. So if you pick up a K at say a random value of K is not a value of the reciprocal lattice. So a vector of the reciprocal lattice can be a vector of the K group, but a vector of the K group is not always a vector belonging to the reciprocal lattice. So there is a superposition, but the main part of the K vectors are not vectors belonging to the reciprocal lattice. And something that we may need to do now is to do the same thing that we did when we considered the vectors in the Sommerfeld picture. In that case, and the same happens here, if you consider this combination, this means that the K values produce a sort of ordered structure in the reciprocal space. And this ordered structure has the same symmetry of the reciprocal lattice, because here we have just a combination of the vectors of the reciprocal lattice. So also in this case, all the possible wave vectors are not, let's say, continuous values in the reciprocal space, but are discrete values that form an ordered structure in that space. So we may ask ourselves, what is the volume of one level? So what is the amount of space that is occupied just by one level? So the volume of one level is let's say, what is the distance between one level and the next? Is the distance that we obtain when we change the value of N1 just by 1, of N2 just by 1, and of N3 just by 1. So the small cell that we obtain is a cell that is described by these three vectors, B1 divided by N1, B2 divided by N2, and B3 divided by N3. So these are the three vectors that identify just one cell. That is the size, let's say, of that cell. In principle, B1, B2, and B3 are not, let's say, the three sides of a cube, because if the lattice is a cubical one, then we have a cubical lattice in the reciprocal space. But if the lattice is not a cubic one, then maybe B1, B2, B3 are not orthogonal with each other. So at this point, a general expression to obtain the volume is to make the vector product between two vectors and make the scalar product with the third vector. So we have B1 divided by N1, scalar product, B2 divided by N2, vector product, B3 divided by N3. So again, this reduces to the volume of the cube if we have three vectors orthogonal with each other. But in case that is not the situation, I now just rewrite everything. So the volume is B1 divided by capital N1, and then I have B2 divided by capital N2, factor product B3 divided by N3. The upper part of that is just the volume of the primitive cell in the reciprocal space. And the volume of the primitive cell in the reciprocal space is 2 pi to the power of 3 divided by the volume of the primitive cell in the direct space, and then divided by N1 times N2 times N3. So this is the volume of the primitive cell in the reciprocal space. This is the total number of ions. So if I multiply the number of ions in the X, Y, and Z direction, I have the total number of ions that build up the lattice. So the meaning of that is the volume of one level is just n total times smaller than the volume of the primitive cell. So the conclusion is in one primitive cell, you may have a number of levels equal to n total. So the number of levels in the primitive cell is equal to n totals. So the number of levels that can be hosted in one primitive cell in the reciprocal space depends on the number of the ions. If the number of levels is equal to n total, the number of electrons can be hosted in the first in one primitive cell is equal to twice n total, because we need to consider spin up and down the fact that one level may host 2 electrons at maximum, and so that is that the number of electrons is twice the number of levels, and that is even. So an even number proportional to n total, and that's important. So please remember that when we will discuss later the properties of the electrons in the system. So again, in this case, the situation is similar somehow to the situation in the Sommerfeld case, apart from this last conclusion, because if you remember, the volume of one level in the Sommerfeld picture was equal to 2 pi to the power of 3 divided by the volume of the solid. And in this case, we have 2 pi to the power of 3 divided by the volume of the primitive cell in the direct space times the number of ions. Since the primitive cell is the cell that you may translate in space over all ions, so to fill the volume of all the solid, then n total times V is equal to the volume of the solid. So it's the same expression, just written using 2 different approaches. In the Sommerfeld case, the approach where there's no lattice. In the block situation, the approach where we have the lattice. So, but the conclusion is exactly the same. So this gives us an indication concerning the structure of the K vector, of the K wave vectors. So an indication of how to express an arbitrary vector belonging to the reciprocal space. And we will see that later, but the conclusion is the same conclusion that we obtained in the Sommerfeld picture. So the spacing here is even more clear if you consider the x direction. The vector that spans the x direction in the reciprocal space is B1. The minimum variation of K in the x direction is B1 divided by N1. That is the number of ions in the x direction. So this means that the value of k in the x direction changes of an amount that is equal to the amount of a primitive vector divided by the number of ions in that direction. As, let's say, more or less the number of ions is of the order of, if we have a cubic meter, is of the order of 10 to the 28. So if N1 is more or less the square root of that, the cubic root, sorry, of that, N1 is of the order of 10 to the 9, 10 to the 10. So this means that the minimum variation in K is equal to B1 divided by 10 to the 9. So a very, very small variation with respect to the size of the primitive vector. So also in this model, we may suppose that even if K is actually a discrete parameter, so that should not be, is not a continuous parameter in principle, but just a discrete variable, then also in this case, we may suppose that K is a continuous variable. So at the end, in any calculation, I will use K as a continuous parameter. I will evaluate integrals. I will write functions as depending on K, as if K was a continuous parameter, as that was obtained in the Sommerfeld picture. An additional comment on K is the following, and comes from the a demonstration of a block theorem. Then I will not make the full demonstration. I just write the starting point and the final conclusion, because I know that many of you have already seen the demonstration of the block theorem. In case someone has not seen that, please just let me know, and then I will give indications concerning the demonstration and where to find that. And the idea is the following: when you demonstrate block theorem, there are two approaches presented in the textbook. One is related to the translation operators. The other is related to the solution of the Schrödinger equation. So the solution of the solution of this equation. In this picture, what you try to do is to, let's say, use a general expression for psi. So the initial step is just to say, okay, I don't know what is the structure of psi. I use the more general expression that can be produced using what I know. The only thing I know is that the K-wave vectors populate the reciprocal lattice, the reciprocal space, using this the expression that we saw before. So they are proportional to the primitive vectors apart from the N1 divided by capital N1 coefficient. So one just supposes that the arbitrary wave function that should be the solution of the Schrödinger equation can be written as a combination of plane waves. I use M as a wave vector just to distinguish that from K. Regarding U, also U can be expressed in terms of plane waves, but in this case we know that U as a periodicity, because that is the expression of the potential of the lattice, and thanks to that, that is expressed as a combination of vectors. So M in this case has to follow the results of the Bohr von Karman boundary conditions. K in this case is a vector of the reciprocal lattice. So capital K is a vector of the reciprocal lattice, while M is just one of the vectors that comes from the application of the Born-von boundary conditions. What one finds during the calculation is that M may be written as Q minus G, where G is a vector of the reciprocal lattice and Q is a vector coming from the Born-von conditions. Just to make an example of who G may be and who Q may be, if we suppose, just to make a picture that is simple, to be in a cubic lattice, then if we have a cubic lattice, the lattice in the direct space is cubic and the lattice in the reciprocal space is cubic. So I just need to represent here squares to to display the lattice. So if this is if these are all the cells in the reciprocal space, cubic cells, and then for instance this is M, so an arbitrary vector in the reciprocal space, then I may write M as G in this case. I may use this representation. I just write, okay, Q plus G, so it's easier now to distinguish, to represent that. So in this case, the let's say G is the vector that brings us from the origin to the cell where the point of Q is located, sorry, the point of M is located, and then Q is the last step that joins the origin with the point of M. In case, if we write M as Q minus G, just to make the same, yeah, this is you may see things in this way. So put yourself in the center of the cell where the point of the vector is. Then Q is the vector that joins the center of the cell with the point of the vector M, and G is the vector that brings you from the center of that cell down to the origin of the space. So in both ways, G accesses the cell where the point of M is located, and then Q is just the final difference between the center of the cell and the point of vector M. So this means that whenever you, let's say, every time you have a vector in the reciprocal space, you may use this combination to write the expression of M. If you use that combination, what is found is that the general expression for the electronic wave function is can be expressed as a combination of plane waves having this structure. So we have coefficients and the wave vector that are always in the form Q minus K. And what is the important point concerning Q? Due to this definition, Q will always belong to, let's say, the primitive cell that is located at the origin of the space, because the modulus of Q will be always within, sorry, the size of Q will be always within one cell. So the vector M here, the vector M in this expression can be a vector that joins many different cells. So no limitation concerning M. But Q is, due to that definition, a vector that for sure is within one cell. So due to the fact that you may, in general, let's say all the cells are equivalent with each other. So there's no one, the best primitive cell or the worst primitive cell. So in this picture, you may consider that to choose as a reference the cell that is at the origin, so the first primitive cell, let's say, and you may always consider that Q is within that cell. So that Q will never exit that cell. And the cell that is located at the center of the space is called the first Brillouin zone. So that this cell here is the first Brillouin zone. So the conclusion is Q in that expression is always a vector belonging to the first Brillouin zone. And that will be the zone that will be used as a reference zone for all the space. The important conclusions that we may obtain from this expression is that psi of R is something that depends on Q. So here we may put Q as a label, and due to the fact that Q is a vector belonging to the first Brillouin zone, we may write down that the solution of the Bloch theorem is a solution where the Q wave vector is always belonging to the first Brillouin zone. And if we rewrite, here there's an R missing. And due to the fact that Q does not depend on the summation over K, where K is a vector belonging to the reciprocal lattice, if you take Q out of the summation, you will have e to the I Q R sum over K of CQ minus K e to the minus I K R. And if you see, this is the structure of the electronic wave function that solves the Schrödinger equation. We just need to demonstrate that this is periodical. So we just need to demonstrate that this is the equivalent of U of Q, U of R of Q. And actually, if you replace R with the R plus capital R vector of the Bravais lattice, in the phase, we have e to the minus I K R plus capital R. Now, as a definition of vector belonging to the reciprocal lattice, we have that e to the minus I K times capital R is equal to 1. And this is the definition of the reciprocal lattice. So at this point, this is just equal to the minus I K times R, so the initial phase. So this means that the second part of this summation actually has the same periodicity that is required to be the modulation of the phase obtained by the Bloch theorem. But the important thing that I wanted to stress using this expression is the following. If we replace Q of R by Q plus G, where G is a vector belonging to the reciprocal lattice, then what we have is a summation over K of Q plus G minus K, Q of Q plus G minus K, and then I have e to the I q plus g minus k times r. But since if k is a vector of the reciprocal lattice, also g minus k is a vector of the reciprocal lattice. If I call g minus k prime, then this is equal to a summation over k prime of c q minus k prime e to the I q minus k prime times r. So the conclusion is that the electronic wave function has the same periodicity of the reciprocal lattice, and this is rather important. So psi of q of r in the reciprocal lattice is periodical terrible, has the same periodicity of the reciprocal lattice. So psi of q plus g is equal to psi of q of r. Since to each wave function you have a value, there's a correspondence between wave function and energy value. So if I call E of q plus g the energy value corresponding to psi of q plus g, and E of q is the energy value corresponding to psi of q, then these two values has to be equal. So also the energy has the same periodicity of the reciprocal lattice. Due to that, we may actually use just wave vectors or crystal momenta belonging to the first Brillouin zone, because anything that happens in all the other points of the reciprocal space can be obtained but just by knowing what happens in the first Brillouin zone and then applying a translation. So the idea is from now on, we will always refer to Q values that belong to the first Brillouin zone as if we know what happens in the first Brillouin zone, we know what happens in all the reciprocal space. So from now on, we will just concentrate on that zone. Please keep that in mind, as that will have a consequence in some situations. So this choice will have an effect on the results that we will obtain, in particular concerning conductivity and on the properties of the electrons. So that is important. It's an important reference. So once we have chosen that zone, we represent Q only in that zone, and all the spaces, all the points in the reciprocal space are obtained by, sorry, all the physical properties, the reciprocal space are obtained by the properties that we already know in the first Brillouin zone. Okay, now it's 11:30, so in a while Professor Guidozzi will be here. So I stop now the lesson. I will go on tomorrow morning to discuss the consequences of the Bloch theorem. Are there any questions or comments concerning this part? Okay, if there are no questions, now I will stop the registration